Sometimes we have functions that look like this. The cos of x squared. Now there are immediate things that are different about this than the straightforward cosine function. It's cos of x squared, not just cos of x. And so we call this function of a function. Y equals a function of another function. Now in this case, the function f is the cosine function and the function g is the square function. Or we could identify them perhaps a bit more mathematically by saying that f of x is cos x and g of x is x squared. Now, let's have a look at another example of this. This time we'll turn it round, so to speak. Let's have a look at cos squared x. Now, how is this a function of a function? Well, let's remember what cos squared of x means. It means cos x squared. Cos x multiplied by itself. So now, if we look at our function of a function, let's see what we can do to identify which is f and which is g of x. So here we are squaring, so it's the f is the square function, and inside the square function, the thing that we are actually squaring is g of x, namely cos x. So here the f is the square function and the g is the cosine function. Or, to write it down more mathematically, f of x is x squared and g of x is cos x. Now, how do we differentiate a function like cos squared x or a function like the cos of x squared? What do we need to do to be able to differentiate something that is a function of a function? To do that, we need to do two things. One, we need to substitute u equals g of x. This would then give us y equals f of u, which of course is much simpler than f of g of x. Next, we need to use a rule or a formula that's known as the chain rule. The chain rule is quite simple. It says dy by dx is equal to dy by du times du by dx. Notice it looks as though the du's cancel out. If these were fractions, which they're not, it looks as though they might cancel out. And that's a way of remembering it. So this is how we're going to approach it. Substitute u equals g of x, and then apply this rule called the chain rule in order to find the derivative. So let's take a number of examples. And the first one we'll take is the very first example that we looked at, and that was y equals cos of x squared. So our first step was to put u equals x squared. And then y is equal to cos u. Now, the chain rule says dy by dx is equal to dy by du times du by dx. So we need du by dx. Well, that's 2x. We differentiate this. We multiply by the 2 and take 1 off the index. That leaves us 2x. And we need dy by du. And the derivative of cos u is minus sine u. So now we need to put these together. Dy by dx is equal to dy by du minus sine u times du by dx, which is 2x. Now, this is all very well, but really we'd like to have everything in terms of x. And here we've got u. So we need to undo this substitution. If we put u equals x squared, we now need to replace the u by x squared. And so we write minus 2x, I'm bringing the 2x to the front, sine of x squared. Now they're all done like that. What I'm going to do with all the next examples that I do is I'm going to put this differentiation of the two bits up here with these two bits. Let's have a look at the other one that we had. Y equals cos squared x. And let's remember that meant the cos of x all squared. So that this is now the g of x. And so we will put u equals cos of x, and then y is equal to u squared. I can calculate du by dx, that's minus sine x, and I can calculate dy by du, that's 2u. We'll write down the chain rule. Dy by dx is dy by du times du by dx. And now we can substitute in the bits that we've already calculated. Dy by du is 2u times du by dx, which is minus sine x, equals. Now, again, we want this all in terms of x, so what we have to do is reverse the substitution. We put u equals to cos x, and now we need to undo that by replacing the u with cos x. So bringing the minus sign to the front, minus 2 cos x sine x. Let's take another example. Y equals 2x minus 5, all raised to the power 10. Now, it might be tempting to say, well, surely we could just multiply out the brackets. But this is to the power 10. To multiply out those brackets would take us ages. And there's all those mistakes that could be made in doing it. Plus, when we differentiated it, we may not have the best form for future work. So let's use function of a function. So here we will put u equals this bit here inside the bracket, 2x minus 5. And then y is equal to u to the power 10. I can now do the differentiation of the little bits. Du by dx is just 2, the derivative of 2x just giving us 2, and dy by du is 10. We multiply by the index, u to the power 9. We take 1 away from the index. And now we can put this together using the chain rule. So dy by dx is equal to dy by du times du by dx. Substituting our little bits, here's dy by du, 10u to the 9th, times 2 du by dx. 2 times 10 is 20, and I want u to the power 9. And I need to get this all in terms of x, so I need to replace the u here by the 2x minus 5. So that's 2x minus 5 all to the power 9. And that's a compact expression for the derivative. think what it would have been like if I had to expand the brackets and differentiate each term. I want now to take another trig example and then develop that trig example a little bit further to a more general case. So we'll take y equals the sine of 5x. Very easy here to identify the g of x. It's this bit here, the 5x. So we'll put u equals 5x. And then y will be equal to sine u. Differentiating, du by dx is equal to 5, and dy by du is equal to cos u. Put the two bits together with the chain rule. Dy by dx is equal to dy by du times du by dx. Dy by du is cos u times by, and du by dx here is 5. So let's bring the 5 to the front, 5 cos of, and now let's reverse the substitution. U is equal to 5x, so we'll replace the u by 5x. Now, notice how that 5 here and here has apparently appeared there. And it did so because the derivative of 5x was 5. So the question is, could we do this with any number that appeared there in front of the x, be it 5 or 6 or a half or 0.5 or, for that matter, n? So let's have a look at y equals sine nx. U equals nx, that's our substitution, and then y is equal to sine u. We can differentiate the u with respect to x, and the derivative of nx is just n, because n is a constant, a number, and dy by du is equal to cos u. We can now put this back together again. Dy by dx is dy by du times du by dx equals dy by du is cos u times by du by dx, which is just n. So let's move the n to the front. That's n cos nx. So the n's have behaved in exactly the same way that the 5's behaved in the previous question. And of course this means now we're in a position to be able to do any question like this simply by writing down the answer. So if we're just going to write down the answer, let's take y is sine of 6x. And then dy by dx is just 6 cos 6x, just by using the standard result that we had before. Similarly, if we had y was equal to cos a half x, well, just because it's cos, it's not going to be any different to sine, really. And so dy by dx is equal to 1/2, and the derivative of cos is minus sine a half x. Now, let's take one more example in this particular style. So we'll take y equals e to the x cubed. And here, this x cubed is our g of x. So we will put u equals x cubed, and then y will be equal to e to the power u. We can differentiate, so du by dx is equal to 3x squared. We multiply by the power and take 1 off it. And dy by du is equal to e to the power u. We differentiate with respect to u. The exponential function is its own derivative, and so it stays the same. Bringing those two bits together to give us dy by dx through the chain rule, dy by dx is dy by du times by du by dx. dy by du is e to the power u times by du by dx, which is 3x squared. Move the 3x squared through to the front, e to the power, and now we made the substitution that gave us u. We put u equals x cubed, and now we need to reverse that substitution and replace u by x cubed. So, let's have a look at what we've got here. E to the x cubed. Now, if we think of this as e to the u, then e to the u is just the derivative of the f with respect to u, because the exponential function is its own derivative. And here, the 3x squared is simply the derivative of u with respect to x. In other words, it's the derivative of g of x. Now let's see if we can put that together for a general case. So, we've got y equals f of g of x. And we're putting u equals g of x. And our chain rule tells us that dy by dx is equal to dy by du times du by dx. Equals. Let's start here. You remember that in most of the examples that I've done, I've been pushing the result of du by dx forward to the front of the expression. So let's do it to begin with, instead at the end when we've been simplifying. So du by dx, this is the derivative of g of x. So that's dg by d of x by dx times by, and this is dy by du, so that's the derivative of f of g of x with respect to u. Now, can we use this? Let's have a look at an example. Y equals the tan of x squared. And so dy by dx is equal to, well, this bit here is the g of x, so we need its derivative, and we're going to write it down at the front. Well, that's easy, that's 2x. And now we need to differentiate tan as though this was tan u with respect to u. And the derivative of tan is just sec squared, and then we need to put in the g of x, sec squared, x squared. Notice how short this is, 2 lines. Let's just look back at the example that we did before, and it took us all of this. What we've done is we've contracted this whole process to one that takes place in our head. It's quicker. You can still do it this way if you like, but if you can get into the habit of doing this, it's much quicker. So let's have a look at some examples and try and keep track of what we're doing. So let's begin with y equals e to the 1 plus x squared. And dy by dx is equal to, well, we can identify the g of x, it's this up here, the power of the exponential function. And so if we differentiate that, it's 2x. And now we want the derivative of the exponential function. It is its own derivative. So that's e to the 1 plus x squared. Able to write it down straight away. Let's take y equals the sine of x plus e to the x. dy by dx is equal to, well, here we can identify the g of x, so we want the derivative of this to write down. The derivative of x is 1, the derivative of e to the x is just e to the x, times by, and we want the derivative of this as though this were u, and the derivative of sine is cos, and then x plus e to the power x. We take y equals the tan of x squared plus sine x. dy by dx is equal to, identify the g of x, that's this lump here, the x squared plus sine x, differentiate it, 2x plus cos x, and now the derivative of tan, as though it were tan of u, well, that will be sec squared. But instead of the u, we want u is g of x, which is x squared plus sine x. Y equals, and this time we'll have a look at one that's got brackets and powers in it, 2 minus x to the 5th, all raised to the 9th power. dy by dx is, got to identify the g of x first, and the g of x is this bit inside the bracket, the 2 minus x to the power 5. So we need to differentiate that first, so that's going to be minus 5x to the power 4. Remember, the derivative of 2, which is a constant, is 0, and then multiply by the 5 and take 1 off the index. So minus 5x to the power 4. Now we've got to differentiate to the power 9 as though it was u to the power 9. Well, that would be times by 9. And then instead of the u, we want the 2 minus x to the 5th, and we take 1 away from the power, and we get that. Little bit of tidying up to do here, because we've got a multiplication that we can do. Minus 5 times by 9, minus 45, x to the power 4, 2 minus x to the 5th raised to the power 8. Take one final example. Let's take y equals the log of x plus sine x. We can identify this as our g of x. So dy by dx is equal to, we can write down the derivative of this, 1 plus cos x times by, and now we want the derivative of log. Well, the derivative of log of u would be 1 over u. So this is 1 over, and this is the u, or the g of x, 1 over x plus sine x. And it'd be untidy to leave it like that, so we move that numerator 1 plus cos x, so it's more obviously the numerator of the fraction. So what we've seen there is the use of the chain rule, but then modifying it slightly so we get used to writing down the answer more or less straight away. You can still use the chain rule, you can still do it at full length, but if you can get into the habit of doing it like this, you'll find it quicker and easier to be able to manage. And more complicated problems will be easier to do if you can short-circuit some of the processes.